What's up, y'all? I'm Tom, and this is Like a Math Class. In this video, we're going to talk about U-substitution. Now, U-substitution is often one of those first stumbling blocks with integration. You're starting to feel good about integration. You've got the power rule. You've got maybe you've got some of your special case integrals that you know. But this is going to be where you have to start looking at new strategies for integrating. And this is the beginnings of where integration can start to get really tricky. But I want to try and break it down for you to make it as easy to understand as possible. Let's get to it. So as we integrate with U-substitution, I want to start by looking at just a general composite function. I don't want to think about integration yet. I want to think about what happens if we take the derivative of a composite function. Now, if we've got f of g of x, and we're going to take the derivative of this function with respect to x, what's going to happen is we need to take the derivative of the outside. We're going to take the derivative of the outside, and then we're going to multiply that by the derivative of the inside. When we do that derivative, we kind of see that we've got something inside. We've got like an original function inside here, and then we've got a derived function out here. Now, if you're watching an integral video, you've probably already done your differentiation, but if you need a refresher on the chain rule, make sure you check out this video right here. Now, let's say we want to now integrate this function and we want to go back here. So we want to take this thing and we want to get back to our original function. Well, that's going to look a little different. So now what we have is the integral of some function times the derivative of an inside function with respect to x. Now, I left off the prime here because you're generally not going to see this outside piece as a derivative. But what you will see is you will see that this piece, this inside piece, kind of lines up with this outside piece. So you're going to see that there is a derivative of a function within here. So here we even see there's a derivative with a piece that with a function inside of something else. So the idea of U-substitution is to convert all variables to U from whatever other variable was used in the function. So that means if here we've got d of x, if we're integrating with respect to x, then we want to change all of these x's to U. If maybe you were doing something with respect to time, then you want to change the time to a variable of U. And we're going to substitute that U value in. And the key to recognize this, is that there is an inner composite function and that the multiple of the derivative of the inner function is also contained in the integrand. Now, the integrand is the actual thing that you're trying to integrate. So in this case, the integrand is all of this. So here, I've rewritten this one more time because what we're going to do is we are going to take this piece right here and we're going to call this U. So we're going to make U equal g of x. And then what we're going to do is we're going to take g prime of x, or in other words, the derivative of U. And the derivative of U with respect to x is going to be g prime of x. And we're going to take this dx, we're going to move it to the other side of our equation here, and we're going to say du is equal to g prime of x dx. And you're probably saying to me, now wait a minute, that's not a fraction. We can't multiply both sides by d of x. And you're right, we really can't. But what we're doing is we're changing all of our variables to u. So we're really just saying, all right, this derivative of u is g prime of x. And that's with respect to x. So we're kind of cheating a little bit, but we're not. We are, but we're not. We are, we're not. So this whole thing then becomes du. Now, what that turns into, you'll like this, is we're going to integrate f of u with respect to u. Yes, we're going to integrate f of u. I thought you might like that. So how does all of this work? It's best described with an example. So let's look at an example together and see if we can map out how this U-substitution works. So here we've got the integral of, here we're trying to find the integral of 3x squared plus 5x to the fourth power and 6x plus 5, all with respect to x. As we mentioned, the key is to recognize that there's an inner composite function. So here I've got something to the fourth power, so that means this piece is inside of this fourth power. So this would be considered an inner function. Now, so my first clue would say, all right, I want to consider that to be u. And so if I make u 3x squared plus 5x, then the derivative of u with respect to x is 6x plus 5. Oh, wait a minute. Check this out. 6x plus 5 is right there. And if we multiply both sides by dx, these things simplify out, and now we have du is equal to 6x plus 5 with respect to x. Look at that, this thing here. So this is all going to turn into du, and this is all going to be u. Now, most of my students start saying, well, wait a minute, what is this du of dx? I don't understand what that means. Let me take you back to when you first started doing derivative. If we had something as simple as y equals x squared, then when we took the derivative of this, we said the derivative of y with respect to x is equal to 2x. That's really all that this du of dx is saying. Is this just saying, hey, we're going to derive this function u, we're going to derive this function u with respect to x. We're going to derive this function y with respect to x. That's what this thing means. So don't get too tripped up on this, even though most people when they first see it, they're like, wait a minute, I don't understand what's going on there. Now you understand what's going on there. So now as I rewrite this whole function, I'm actually integrating u to the 4th power with respect to u, right? Because all of this is represented by du. This whole inside piece is represented by u. So now I'm just integrating u to the 4th power. That's super easy. So the integral of u to the 4th power is 1 over n plus 1, 4 plus 1, u to the 4 plus 1. And that's going to be plus c, right? We always have to put our plus c on there. Don't forget about the plus c. So we've got 1/5 u to the 5th power plus c. Of course, we're not talking about u. We're talking about this whole thing here. So we've got 1/5 of 3x squared plus 5x to the 5th power plus c. Now, we're done. It may not look like we're done, but this is our integrated function. But before we go on, let's check the derivative of this. Because if we take an integral, if we find an integral of a function, the derivative of that should take us back to the original integral. Since I'm generally really good at derivatives, since you are probably pretty good at derivatives, that's the thing you learned first, that's the pattern you learned first, that comes a little bit easier now. So let's check our integral with our derivatives. So if I'm trying to find the derivative of 1/5 3x squared plus 5x to the 5th, we know the power rule, or the chain rule, says take the derivative of the outside. So this 5 comes out here and we subtract 1 from that. So 1/5 times 5, well, that's going to be 1. And then we're going to be left with 3x squared plus 5x. We already said that goes to the 4th power. So that's the derivative of the outside. Now we got to take the derivative of the inside, which is going to be 6x plus 5. And look at that. This thing here matches what we had right there. So we're good to go. That's all that U-substitution is. Backwards chain rule. Let's look at one more example real fast. But before we do that, hit subscribe. That way you can be up to date when new videos are posted. So here we got the square root of 2x plus 1. Now, I already see that 2x plus 1 looks like that's going to be the u piece. That's inside the square root. That makes a little bit of sense. But I actually don't like integrating a square root. So I'm going to change this to 2x plus 1 to the 1/2 power with respect to x. This is still my u value right here. So now I'm going to take the derivative of u with respect to x, and that's going to be a value of 2. I'm going to multiply both sides by dx, and that leaves me with du equaling 2 dx. So this over, whoa, wait a minute. There's no 2 over here. Here, if I want to substitute du in, I've got to have 2 dx, but I don't have 2 dx's. I've only got 1 dx. So let me get rid of this 2. So I'm going to divide both sides by 2, which leaves me with 1/2 du equal to dx. Okay, so now here, this dx is going to become 1/2 du. So all I did was I flipped what my substitution is going to be. So instead of it being du equaling a whole chunk, now I've got dx equaling a whole chunk. So I've got 1/2 du. So as I rewrite this, that's going to give me the integral of u to the 1/2 power times 1/2 du. Now, we know if we're multiplying a constant when we're integrating, we can just bring that constant out to the front. So we've got 1/2 integral of u to the 1/2 power with respect to u. Okay, again, now we're just down to our basic power rule. So as we integrate, we've got 1/2 times 1 over 1/2 plus 1 u to the 1/2 plus 1 plus c. Okay, 1/2. This is 1 over 3/2, which is going to change to 2/3 u to the 3/2 plus c. All right, so our 2's are going to simplify and we're left with 1/3 u, which is 2x plus 1 to the 3/2 power plus c. And this is my solution. Again, let's check real fast our derivative to see if we did the right thing. Hi, Blanca. Oh, hello. It's my dog. So let's check the derivative. If we've got 1/3 2x plus 1 to the 3 over 2 power, this thing is going to get multiplied out here. So we're going to take 3 over 2 times 1/3 2x plus 1. 3/2 minus 1 is 1/2 times the derivative of the inside, which is 2. So this 3 is going to simplify, this 1/2 is going to simplify with that, and we're left with 2x plus 1 to the 1/2 power. So we did it. Yes, it feels good. Now in our next videos, we're going to start looking at some of our other special case scenarios where we're integrating with this chain rule idea or this U substitution idea. So if you found this video helpful, give me a thumbs up, like the video, and I'll see you in the next one.